pleasure to be with you again. The objective of this presentation is to explain the main facility we have at HydraFACT and the modeling facility and the technology that we use. We have more than 70 high-pressure autoclaves, and these are very useful in measuring hydrate formation, hydrate dissociation, to some extent because they have a torque measurement at the top here. They are useful for measuring the apparent viscosity. Yeah, so they have a torque measurement. This one is also a visual autoclave, which has torque measurement device here. This one is different. This is what we call it rocking cell. And I discuss what is the benefit of each one. And we have different metallurgy for different system, different volume, you know, and we can have also pressure. Yeah, the volume, we can go to 2000 bar, which is around 30,000 psi, and different volume. Yeah. So what we do with them, measuring hydrate phase boundary, evaluating effect of various hydrate inhibitor, salt or organic inhibitor, evaluate the performance of kinetic hydrate inhibitor, testing performance of antiagglomerant, visual observation of hydrate formation and taking picture, and variable volume. You know, this rocking cell has a moving piston, so we can change the volume while keeping the composition constant. And that is sometimes very useful. And I explain this a bit more here. So these are largest size of this Rex, and you can see here the visual window that we can see inside the cell. And this is called blind autoclave, visual autoclave, and rocking autoclave. And as I mentioned, one of the area of activity for us to build this equipment. For example, now the company wants 2 of these blind autoclaves. So we can build them, and because we do the tests ourselves, we use this equipment ourselves, then we make sure that, you know, they are very useful for the client. So now a little bit of theory. The state of a compound is solid, like here. Okay. That molecules attach to each other, and the point of attachment is fixed. They have their own shape. The next one is liquid, where the molecules are almost attached to each other, why is called incompressible or non-compressible, but they can move and rotate here. So they take the shape of the container. The next stage, if you increase energy, become gas or vapor. In vapor, each molecule separates, and therefore some other molecule can go inside them, and they fill the whole volume. They fill the whole volume. Liquid has a volume, but can take shape of the container, but has a limited volume. Solid, it has its own shape. You can't change, look at the cube of ice. If you put it in a glass, it has its own shape. The next stage is that the molecules are moving so fast that they collide with each other and remove the outer layer electron, and that is called plasma. Probably you are aware that what we see in sky is all plasma states. We don't see solid states, or except, for example, here we see in our galaxy or our solar system. Water is a very strange compound. It has 6 electrons. It has totally 8 electrons. 2 electrons in the S layer, 6 electrons in the P layer. And here, the P layer needs 8 electrons. So it forms a cloud of 2 electrons here, 2 electrons here, and 1 electron shared with hydrogen. This is oxygen. Another electron shared with hydrogen. So now this area becomes 2 electrons here, and this becomes 2 electrons here, so it is complete. And hydrogen needed 1 electron, so hydrogen is complete, but electronegativity of oxygen a lot larger than hydrogen. So most of the shared electron will rotate around the oxygen. So hydrogen have a positive charge, and oxygen would have a negative charge. This is called hydrogen bonding. And for that reason, water is very stable. And, the melting point of water is, boiling point of water is 100 degrees, but boiling point of methane is minus 162 Celsius. And that's because of hydrogen bonding. So this is, you see, the shape of cavity that has formed in the water. Now, gas hydrates are crystalline compound where the gas or former that normally are gas generally are trapped in the cages which has been formed by hydrogen bonding water, which is host. So water is the host and the gas is the guest. They are formed as a result of physical combination, the stabilization of the van der Waals forces. No bonding exists, and gas molecules are free to rotate. And unlike inorganic hydrate, which has a fixed formula, gas hydrates do not have a fixed formula. The amount of water can change with respect to pressure and temperature. But for example, in organic, the amount of water is fixed. Now, how hydrates form and a little bit can be explained here. So the necessary condition for hydrate formation is presence of water or ice, because that is required for hydrogen bonding here. Then suitable size gas and liquid molecules as gas. This is host, this is gas. And suitable temperature and pressure condition. Pressure and temperature is shown with this graph. And you see that at lower temperature, the pressure required for hydrate formation is less. Higher temperature is higher pressure. So to the right, we do not have hydrate. To the left, we have hydrate. What determines the location of this curve is the composition of the gas and composition of water. And I'll explain how. You know that two molecules, they interact with each other. But the level of interaction depends on the distance and the physical property of the molecules. So if two molecules, one is here, one is here, they are far apart and they don't interact with each other, and you see the interaction is zero. As they get closer to each other, they shift the electron band. So the shape of the curve, the shape of the molecule will change. One part become positive, one part become negative. And the same with this molecule. So these two molecules will attract each other. So this is the attraction. And there is an optimum point for attraction. And then after that, when they get even closer to each other, they will repel each other. So you can see here. So there is an ideal size or distance that will let the molecule to get attached with each other, okay, or get close to each other. Here in hydrate, the molecule is not moving. Oxygen is not moving. So the attraction depends on the size of molecule. If it is nitrogen, very small molecule, the distance is too large. Therefore, it's difficult for nitrogen to form hydrate. But for propane and isobutane, they are ideal. Isopentane is in hydrocarbon is probably the best hydrocarbon to form hydrate. But isohexane is a bit big. So it goes to the repulsion. So you see that how the composition of the gas play a role on this hydrate phase boundary. The other factor that impact the hydrate phase boundary is composition of water. If you have anything dissolve in water and is not a hydrate former, that will inhibit hydrate formation. So shift the hydrate boundary to the left. Why? Because some of the water molecules become busy dissolving that salt or methanol or glycol. Therefore, less water is available for hydrate formation. So if we have propane or isobutane, the hydrate curve moves to the right. If you have hydrogen, the hydrate curve moves to the left. If you have some salt or chemical inhibitor, the hydrate curve moves to the left. And this is the technique we use for preventing hydrate formation. Now, we have two terms normally. We call it hydrate formation and hydrate dissociation. Hydrate formation, when we have different techniques for testing. This is, as I'll explain later, this is isochoric. Isochoric is when the volume is constant. So when the volume is constant, if you cool the system and we have some gas, so pressure will be reduced. This is pressure reduction because we are reducing the temperature. But you see at a point here, the pressure drops very sharply. This is the point of hydrate formation. And then if you start heating again, and if you join the initial line, and this is the end of hydrate dissociation. We don't use hydrate formation in our calculation because hydrate formation depends how fast you cool the system. What is surface area? Do you have solid particle? What is the volume? What is the mixing rate? So it depends many factors. But hydrate dissociation point, if you measure it accurately, and with technique that I will describe later, it is unique. That is the point when the last crystal of hydrate will melt, and after that, the pressure-temperature relationship is based on gas expansion. Although we use hydrate dissociation point, is a common mistake. We say hydrate formation, but hydrate formation is not used in hydrate calculation. But on the other hand, wax formation will be used for evaluating risk of wax. And I can explain that later. But because, in summary, because the hydrocarbon composition have an exponential decay. So as the carbon number increases, its concentration is reduced. And wax or paraffin start with normal alkane. For example, C40. The amount of C40 is very little. For wax, we get a curve like this. But if you design it on wax appearance temperature, it will be very expensive because you need to consider this much heat or temperature. You need to plan for it. But the amount of wax formed at this point is very little. And mostly it will be suspended. So we don't design on wax disappearance temperature. We design on wax appearance temperature. But for hydrate formed from a small molecule. We always have a lot of hydrate, a small molecule in the system. Therefore, if we miss this point, we can end up forming a lot of hydrate. That's why for hydrate measurement, we measure dissociation point and put that as the basis for our design. For wax, we measure wax appearance temperature and put that as a basis for design. But for phase equilibria, we always have to put hydrate dissociation and the same with wax dissociation, because that's the only point that the system in equilibrium. When you want to form hydrate or wax, you are introducing a new phase to the system. For any new phase to form, we need some subcooling. We need supersaturation. Okay, so that's why when you are, but removing a phase doesn't need supersaturation. Therefore, by removing a phase or melting a phase, we can get, by careful experimentation, we can get very accurate result. Now, this is called subcooling. It's delta T between dissociation point and formation. And I said subcooling depends on the system and procedure. This is called overpressure. All of these two are important for measuring the kinetic of hydrate formation, rate of hydrate formation. But I mentioned that what important for hydrate modeling is dissociation point. Now, how to measure hydrate dissociation point? There are various techniques. One option is hydrothermal. So, hydrothermal, the temperature is constant, and we increase pressure to form hydrate. When we want to dissociate hydrate, again temperature is constant, and we reduce the pressure to dissociate. Now, question, how can we increase or decrease the cell pressure? We cannot remove part of hydrocarbon to reduce and increase because composition change. As we discussed, the composition of hydrate is different from the gas. We can't do that. So the only option would be that we have a variable volume cell. So the system, the composition of system is constant. We increase volume to melt hydrate, we decrease the volume to increase pressure to form hydrate, while the whole system is at constant temperature. How we detect hydrate? How we detect hydrate? That's another problem. Because, you know, you are letting temperature is constant, pressure is changing, so you cannot use pressure, you cannot use temperature, so you need to have visual device that you see hydrate is formed. And we try to avoid visual devices because they can be dangerous. So the other option is isobaric. Isobaric means that the pressure is constant and we change temperature. So, for example, starting from here, we reduce temperature to move inside hydrate phase boundary. If we reduce temperature, the volume is reduced. Pressure will drop. So you need to maintain or reduce the volume to keep the pressure. So again, you need a piston vessel. And again, how we detect it? Again, visual. Okay. This option that we use normally isochoric. That is, the volume is constant. Nothing is added, nothing is removed. Cell volume is constant. We don't keep it, it is constant. Nothing is added or withdrawn from the cell. Then what we do, reduce temperature and monitor pressure. Okay, so reduce temperature. This I show you earlier, and I mentioned that this is isochoric measurement. This is cooling curve, and you see that this part up to here is reduction in volume because of temperature. But how you explain this bit? Sudden change in pressure temperature graph. That is gas taken from the gas phase and trapped in hydrate. As you know, hydrate can store ideally 182 volume per volume. So when hydrate form, a lot of gas is required, so the pressure will drop. So we form hydrate. Now, melting hydrate, we can increase temperature. You see that the pressure will increase. This here, you see that this section is parallel to this section. Can you see here? This from here to here is parallel to this section. This shows that all the water has been converted to hydrate. And therefore, no hydrate is melting at the moment. Only the gas is expanding. But here you see a slope change. That is the point that hydrate is melting in addition to gas expanding. Because if it's only gas expanding, we should have something like this. So this is in addition to gas expanding, we can see hydrate is melting. And here, if you continue here, you come to the point here that the line will join the another slope chain. The heating will join the cooling line. This is the last crystal of hydrate at this point here. This is dissociation point of hydrate. This is dissociation. This is formation. Now, to make sure that your dissociation measurement is accurate, we propose a step heating. I'll explain in the next slide. So to answer the question here, how we detect hydrate formation, we can detect it graphically. So no risk. So we can use blind cell. But also we can use visual cell. So we can see with camera. I mean, we don't look at glass window with naked eye. And we see hydrate formation and dissociation. Okay? Visual cell. But we don't need to visual cell. For using, when we use isochoric, we don't need visual cell. And that improves the safety a lot. But a lot of people prefer to see it. They say seeing is believing. So we get requests for visual cell, we get requests for blind cell or rocket cell. I mentioned to you that we use a step heating. This is predicted hydrate phase boundary. And this is the cooling line. Here we form hydrate. And then we increase temperature to melt hydrate. And you see that for this, a lot of companies and universities, they use continuous heating. We argue that in continuous heating, you are always out of hydrate stability. Instead, what we suggest that do a step heating. You one step, you see that hydrate is melting, pressure is increasing. Next step, you see that you need to give time for hydrate to melt and pressure increase. And then another step, you need to give time for hydrate to melt. And another step, give time, another step, give time, another step is here. And then these are equilibrium points. These are also equilibrium points. When they cross is dissociation point. Okay? This is more accurate. And then we want to create a hydrate curve. Here, you see that we start from low pressure because start from high pressure is not ideal because each time to reach the low pressure, you need to withdraw some component. And then you might have some history of hydrate, so you remove, so the ratio could be different. So here you can see that at starting from low pressure, and cooling down, forming hydrate, and then melting hydrate, and we find this point. 1 point. Then reduce the volume, yeah, or add new raw material. The pressure will increase, and then do another measurement, find another point, and then increase, do another measurement, find another point. And this is 13,000 bar, yeah, another point. I mean, this was the case that we wanted for an unknown chemical. We wanted to see that, you know, how much is the inhibition, and then find the relation between inhibition and adding enough chemical. So that was, but you see that how we measure them. And this is the shape of, you know, internal shape of this cell. You can see that it has a mixer. You can increase pressure, inlet, outlet, and then this is the magnetic motor. We measure torque, and this is impeller. This is a temperature probe, yeah, PRT, and this we have a cooling jacket around it, okay, pressure, and then basically we do test here. You can see here this is a cooling jacket, and this is torque measurement, and this is mixing. Different shape and sizes of mixer we can put in the cell. And then another device that I mentioned earlier is the rocking cell. Rocking cell, basically we have two types of rocking cell. One that the volume does not change. Okay, the volume does not change. We just rock it. Okay. The another one, the volume will change. So this one, you need a cooling jacket here, and then there is a piston. We can inject chemical behind the piston and change the volume. And the rocking mechanism will create mixing. And this is the visual cell, a rocking cell, that we normally use it for evaluation of anti-agglomerant. This is something that we have designed, helical tube mixer. This is in fact a flow loop. In flow loop, what you do, you pump the fluid inside the loop. Here, we push the pipe inside the fluid. So when you push the pipe inside the fluid, is the same shear forces apply, but inside and outside. In a flow loop, only inside. And another good point, instead of having a blade mixer, blade mixer will push all hydrate to the wall. But flow loop, this helical flow loop doesn't do that. So provide you rotate it clockwise this way, and the fluid goes from here, rotate, 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 and come here, and then mix. Okay? So we measure the torque by calibration of this setup. We can measure apparent viscosity. We have tested this against a very expensive fluid and provide good results. So basically what we can do is we can provide this Helical tube alongside the conventional impeller. And if necessary, you can change it and do the measurement. This is the visual cell that we have used it for wax investigation. This is the visual cell that I'm shown the figure earlier. We used it for wax investigation. And this is a barometer. It's a very accurate barometer. We can measure apparent viscosity. We can measure hydrate slurry viscosity. We can measure wax. We can measure the basically force necessary to remove a hydrate blockage or a wax blockage. So can do a lot of work with it. And, this is an interesting setup. Those of you that involved in wax measurement is that an important issue with wax measurement is wax deposition on the wall. A lot of wax measurement devices, they use cold finger. Cold finger is basically you cool down a piece of metal and then measure the amount of wax attached to it. First of all, the temperature difference is not realistic. The cell temperature is around 40, but the cold finger is 4. You don't see such a high temperature gradient in the system. Secondly, is that there is no shear. The shear is just a magnetic mixer at the bottom of the cell. So it doesn't have shear. You can't, while in the shear is an important factor in wax deposition. So we bought this setup that we can coaxial cold finger with shear and temperature gradient. So here, what you can see is a cell, and this is the rotating part that is by magnetic mixer here. It will rotate. And then this is one bath, which is control the temperature of the oil. This is another bath that control the wall temperature. So we can control each of them independently. And then we can adjust the rotation of this. This is rotating. This one is fixed. Rotation, creating different shear. And by adjusting temperature of this bath and this bath, we can follow any pressure and temperature gradient. Pressure is the same, but temperature gradient. Interestingly, we use a study, and conventional cold finger recommended a lot of inhibitor. But when we look at actual temperature gradient, we notice that amount of wax deposited is very little, so we don't need that much inhibitor. And we are able to simulate pipeline condition as is warm and cool down by adjusting the temperature of this bath and this bath. And this is the inner part that the wax is deposited here. We can take it out and remove it. Yeah. And then observe it or measure type of wax, effect of different inhibitor on wax formation and things like that. Another important equipment that we have is quartz crystal microbalance. Quartz crystal microbalance is piezoelectric material. It has a resonance frequency that if you apply voltage to it, it has a resonance frequency. That resonance frequency is a function of fluid viscosity, fluid density, and mass of solid material depositing on the quartz crystal. And because we can detect 1 Hertz, we can detect 1 nanogram, 10 to the power -9. Wax appearance temperature, wax disappearance temperature, and we can also measure effect of inhibitor. And we can do the same with as14 for as14, but we can use this technique, atmospheric one, only titration technique, but we have high pressure one. Here you can see that we can detect wax appearance and wax disappearance. Wax appearance temperature is used for design. Wax disappearance temperature is used for thermodynamic modeling. So quartz crystal microbalance is very powerful. This is high pressure rocking cell quartz crystal microbalance. So quartz crystal microbalance is here. This cell will rock. And then we can, for example, we can see the effect of inhibitor on preventing deposition of wax on the surface of QCM. And you see that there is an optimum point. There is a, 100 ppm is enough. Some people may increase more, but that's waste of money. Okay? But we can see that with quartz crystal microbalance. This is our novel project. Spent a lot of time on this, time and money. It is high pressure QCM, quartz crystal microbalance, with temperature gradient and shear. So the benefit here is that this is a piston vessel. We can change the volume. See that moving piston? We can change what? Ideal for as14 investigation. Because as14, you want to condition the system and you don't want to take anything out or add something. So you can increase pressure by reducing the volume and reduce. Okay. And then you have a mixer with torque measurement. You have an end here that you can cool down, and QCM is attached to this end. So this mixture can create shear. The one bath here create the temperature of the cooling section. One bath is the main cell temperature, and the moving piston will increase, decrease pressure. But as we started the a project, as 14 project with this, and what we are seeing is amazing. And maybe I will share that another point. But this is our latest development. Spend a lot of money, but we are very happy. This is another setup for simulating gas injection to oil and basically effect of gas injection on asphaltene precipitation. And this is the helical tube I mentioned to you. Set up helical tube. And I'm going over the time, but I briefly mentioned here. This is a moving piston, moving sampler, capillary sampler. And here again, you have a visual cell, you have a mixer here, you have cooling jacket, and we can take sample from different phases. We can take sample from water, from hydrocarbons, from gas, and send it directly to gas chromatography. This is a slim tube for EOR study, finding minimum miscibility pressure. So that's the slim tube here. This is live oil. This is a transducer downstream back pressure to maintain the pressure. Here we were investigating effect of carbon dioxide for EOR. And this is toluene, and this is live oil. And this is our core facility for EOR and scale formation, recovery factor. So thank you very much for your attention.